In this video, I'm going to discuss the first problem from our exam 1. This problem involves analyzing the stress elements on a cantilever beam under specific load conditions. The beam is fixed at one end with a downward force applied at the free end. Additionally, there's a torque applied in a counterclockwise direction when viewed from the end where the x-axis points towards you. This setup challenges us to accurately determine the types of stress at two distinct points on the beam, considering their specific positions and the direction of these applied forces. Let's dive into where I initially went wrong in my analysis and how I corrected my approach. The issue started with how I tried to use a previous homework problem for help. That problem had a force going in the negative z direction. I thought I could just turn the beam 90 degrees to make the force go downwards, like the exam. I changed the labels of the stress points to fit this new setup, but I forgot to turn the coordinate system too. So, while I had moved the beam, I left the coordinates the same. This mix-up made my answers wrong because I was looking at everything from the wrong angle. This mistake really showed that I was leaning too much on that old homework and not really understanding how forces work on different parts of a beam. I tried to reuse an old solution instead of thinking through the new problem on my own. From this, I learned I really need to understand the basics of how forces affect a beam, not just try to copy and paste old answers onto new questions. Let's dive into the detailed analysis of this exam's first problem. We're examining a cantilever beam with a downward force applied at the free end and a counterclockwise torque when viewed from the positive x direction. Our objective is to assess the stress types at two specific points, element A and B. Element A, positioned near the fixed end at the top of the beam, experiences significant compressive bending normal stress in the negative y direction. It is subjected to the maximum bending moment due to its proximity to the fixed support. This maximum moment occurs because the entire length of the beam acts as a lever, intensifying the bending effect when the downward force is applied at the free end, compressing the top inward. Element A is also subjected to torsional shear stress. This results from the applied torque, which attempts to twist the beam around its longitudinal axis. When you apply torque, it generates shear stresses within the material that act along the plane perpendicular to the axis of rotation. For element A, this torsional shear manifests in the positive xz direction as it resists the counterclockwise twist induced by the torque. This stress resists the twisting effect, helping maintain the beam's stability. Element A does not experience transverse shear stress because transverse shear stress primarily occurs where shear force is present along the cross-section. Since shear force is highest at the beam's midpoint and decreases to zero at the fixed end in the cantilever, there is little to no transverse shear at element A. Element B is positioned on the side of the beam at the positive z face. This location is crucial as it does not experience the bending normal stress. The bending stress is zero here because element B lies along the beam's neutral axis, where bending stress transitions from tensile to compressive, effectively canceling out at this specific location. Element B does, however, experience transverse shear stress in the positive xy direction due to the vertical shear force component. This is a result of the shear flow due to the load at the free end. Additionally, torsional shear stress impacts this element in the negative xy direction, which was given. It opposes the twisting motion imposed by the torque. Neither element A nor element B experiences axial stress because there is no force acting along the beam's length that would cause direct compression or tension. Additionally, pure shear stress does not occur because there are no opposing in-plane forces acting directly across the face of the beam. The only shear stresses present are due to the transverse shear and torsion. Comparing my original answers to the correct ones, you can see I had many flipped answers. I had a bending normal stress as negative y for B and 0 for A, when in reality it should have been the other way around. The same mistake happened with transverse shear. I put 0 for B and positive xy for A, when in fact B should have been positive xy and A should have been 0. For torsional shear stress, I had also mixed up the coordinate directions. I originally put positive xy for A instead of the correct positive xz. This happened because I didn't pay enough attention to how torque affects the beam's different faces. And then there's my biggest I have no idea what I was thinking moment. I had axial stress as negative y for element A, which makes no sense. Honestly, your guess is as good as mine. I think I panicked and thought, no way we could have that many zeros, so I just threw something in there. In the end, this problem reinforced the importance of carefully analyzing forces and stress directions instead of relying on intuition or past problems without fully adapting them. I made mistakes by flipping values, mixing up coordinates, and second-guessing myself, but working through these errors helped clarify my understanding of stress distributions in a cantilever beam. That wraps up my analysis of this problem. Thank you for watching.